This chapter we will discuss data and plots. Now, a line plot is a diagram that shows the frequency of data on a number line. It's not to be confused with a line graph or line chart. A line chart is, say, time and, I don't know, birds or something. Birds. And you plot your points and you draw a line through them. This is a line chart or line graph. Why they decided line plot is a brilliant term to use for a method of tabulating data or tallying data, I do not know. It's one of those curiosities of mathematics, I suppose. So here we have a table that shows the shoe sizes of students in a class. When you make a line plot, what you do is, okay, 10, and then you make a symbol, in this case an X, here, and 6, okay, X, and you keep going until you have all the data tallied up here. Basically, this is a tally. Except with this sort of tally, you basically have a bar graph. Look, this is the length of the bar. This is the length of this bar. This is the length of this bar. And this is the length of this bar. Kind of like that. So, I guess somebody decided that tallies were not visibly intuitive enough. And that for some reason they didn't want to use a bar graph instead. Even though this is totally just a bar graph, except without the bars filled in. Well, using the line plot in example 1, identify any clusters, gaps, or outliers. Well, there's a cluster around here. Cluster. Actually, there's two clusters. One around shoe size 10 and one around shoe size 6. And there's a gap. And then there's the outlier. Yeah, these two clusters exist for the same reason as how human height is going to generally show a bimodal distribution, i.e. it has two peaks. These two peaks are not necessarily the same height. Humans are not a very dimorphic species, unlike, say, gorillas, where males can be like twice the body mass of females. But we do have some dimorphism, and the result is that you're going to see a lot of bimodal distributions when it comes to physical properties of humans. Like if you wanted a plot of body mass, well, it's still going to be vaguely bimodal, even though with the obesity epidemic in industrialized countries, it's less so than it perhaps used to be. So, use the line plot in example 1. We identified these. Analyze the data by using these values. Well, we kind of just talked through that. So, it's bimodal. The clusters are at shoe size 6 and 10. There's a gap at 12 and 13, and there's one student who has shoe size 14. What is the range of data? The range is from the lowest value to the highest value, 4 to 14. Or if you want a numerical measure of how broad is the range, the width of the range would be the largest data point minus the smallest. In other words, the range would be 10 if you wanted that version of range. Exercises. Use the list below for the number of pets owned by different families and make a line plot of the data. Well, you can't have -1 pet, so 0, 1, 2, 3, 4. There's a family with 6 pets, so there. Okay, 1, cross that out. 0, we make a mark and we cross that out. 2, we mark that. 0 again. 3, 0 again. 2, 1, 6, 0, 0, and 1. So identify any clusters, gaps, or outliers. You'd be like gap at 4 and 5, or because you have a diagram, you can just point it out. Outlier is a data point, for our purposes, that is distant from the rest of the data on either end. Clusters, well, there's a cluster right here. And the only reason it piles up against 0 is because you can't have negative numbers of pets. So, what is the range of the data? The range is from 0 to 6 for a range value of 6. Now let's say we're going to measure central tendency and range. Well, the mean, median, and mode are all measures of central tendency. The mean is the sum of the data divided by the number of data items or data points. So, in other words, the average. Average. The median is the middle number of the ordered data from smallest to largest or largest to smallest, or it's the mean of the middle two numbers. If you have an even number of data points, the median is going to be the average of the middle two. The mode is a number, or numbers, that occurs most often. The mean, median, and mode are measures of central tendency, and range is a measure of how wide the data is spread. Okay, the list shows the number of hours students spent practicing for a music recital. Find the mean, median, and mode of the data. Well, to find median, you have to rewrite it from smallest to largest, or vice versa, so let's do that. 0, 2, 7, 8, 8, 8, 9, 9, 11, 18. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 students. Okay, then you're looking for the median is the average of 8 and 8. So 8. Mode equals 8 as well, because we can see there's 3 8s and nothing else that reaches 3. If you have, say, 3 8s and 3 9s, your mode would be 8 and 9. You would have 2 modes. You can have multiple modes, but you can only have one mean and one median. So 0 plus 2 plus 7 plus 24 plus 18 plus 11 plus 18, 80 divided by 10 is equal to 8. Interesting. The mean also happens to be 8. Well, find the mean, median, and mode for each set of data, round to the nearest tenth if necessary. Mean, you just add them up and then you divide by the number of items. Here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 items. So 27 plus 56. Well, the mean is equal to 375 over 10, which is equal to 37.5. Okay, then, for the median, we need to rewrite this in order. So 19, and the next one up is, well, we see is 27. Oh, 25, okay. 25. Yeah, we should cross those out. And then we have 27, specifically 2 of them. 27. Okay, after that we got 34 and 34. 34 and 41 and 56. 56. Perhaps I should have written a little smaller. Oh well, it can't be helped. Anyway, so there are 10 numbers. That means it's going to be the 5th and 6th one averaged that will give us the median. Median equals 34. And mode, we can clearly see that there are 3 56s, and then there are only 2 27s and 2 34s. So mode is equal to 56. Okay then, for this next one, the mean we'll have to find the total for. So 7 plus 3 plus 12, 22 plus 4 plus 6, so it's plus 10, plus 3 plus 4 plus 8 plus 7. You know what? 3 plus 7 is 10, 4 plus 8 is 12, therefore plus 22 plus last two, 23. So 77. There are how many numbers? There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 numbers. So mean is equal to 77 over 11, which is equal to 7. Now, if we rewrite this in order from least to greatest, it's going to be 3, 3, and 3. 3 and 3. And then 4 and 4. 5, there are no 5, 6. And 7 and 7. 7. 8. 12. 20. Okay. So the median is, there are 11 numbers, so we're looking at the 6th number, with 5 on either side, as the median. Median equals 6. And the mode, the most common number, the one that appears the most times, is obviously 3 here. Okay, what about this one? 1, 23, 4, 6, 7, 27, 5, 3, 4, 6. There are how many numbers? There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 numbers. Mean is equal to what over 14? So 1 plus 23 is 24 plus 4 plus 6, 34, plus 34, because 2 7s is 14, plus 20, plus 5 plus 3 plus 4 plus 6. 3 plus 7 is 10, 4 plus 6 is 10, therefore it's plus 25, plus 7, 11, and 6, that's 24. So 117 over 14. So this is, of course, not a whole number. It's 8, and then 14 times 8 is 112, so 5 over 14 is left. Okay, So let's rewrite this to find the median. We got 1, 2, 3, 4, and 4. Out of these 14 numbers, the median is going to be the average of the 7th and 8th. 1, 2, 3, 4, 5, 6, 7. Oh, hey. Median is once again the average of two identical numbers. Median equals 6. It's going to be between these two. Now the mode, there are two modes here. Because there are 3 6s and 3 7s. 6 and 7. Okay then, what about if you have a bunch of the same number? Well, if you have a bunch of the same number, your mean is that number. Mean is equal to 3. Median, well, it's equal to 3 because if you line these up from least to greatest, they're all the same. So the middle number is the same. And the mode is equal to 3. In a stem and leaf plot, the data are organized from least to greatest. The digits of the least place value are usually the leaves, and the other place value digits form the stems. However, it could be that the digits of the last two place values are the leaves. Like say you got this, 190, 193, and 202. You can organize them like this. Stem, leaf. You can organize them with the stem being 1 and 2, and you got 90 and 93. So in other words, the 190 comes here and breaks up. 193 also breaks up. 202 would be here. Or you could go for stem 19 and leaf 0 and 3. So like this. 19, 0, and 3 at the end. And for 20, you got 2 at the end. Well, actually, this is the 190s and the 200s. So, make a stem and leaf plot of the data below. Then find the range, median, and mode of the data. Well, we see that we got numbers in the 30s, in the 40s, and in the 60s. So, we're looking at... Yeah, there's only one choice for stem here, the tens digit. Unlike with that example I just gave, where there were two choices for stems. So we got the 30s, the 40s, you got to put in the 50s, even though there's nothing there, and the 60s. So, 30s, we got 35, 36, 37. Do we have anything less than 35? No. So, 5, 6, 7, 6, and 7. And the 40s, we got 42, 42, and 42. And we don't have any 40s or 41s, so 2, 2, 2. And we got 45, 45, 46, and 47. So 5, 5, 6, 7. And then we got a 63 down here. Okay, so find the range. Range. In this context, the range, you can say the range is from 35 to 63, but they actually mean the numerical range, which is 63 minus 35 equals 28. Minus 35 equals 28. Now the median, how many data points are there? Oh, it's pretty easy to count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, 11 data points means that the number 6 one is going to be the median. Median. 42. The mode of the data. So the most frequently occurring number is, of course, you can see that there are 3 42s. Mode 42. Okay, so let's make a few other stem and leaf plots. Then find the range, median, and mode of the data. Fortunately, we don't have to calculate means, so it's not that button mashy. Stem and leaf plot. Well, we got less than 10, so 0, 1. We got the 10s, and we got the 20s here. Okay, so stem 0, 1, and 2. And leaf. So 0, 1. And stem, got 1. That means 15, 16, 16, and 19. 15, 16, 16, and 19. Okay, what about the 2s? You got 25, 28, 27, and 28. So 25, 27, 28, and 28. Okay, then. Find the range. Range is going to be 28 minus 1 for numerical range. Range numerical is 27. Median is, well, it's going to be the 5th number because there are 9 numbers. So that's 19. And mode. Well, there are 2 16s and there are also 2 28s. So modes 16 and 28. Okay, what about this? This is not a great set of data for a stem and leaf plot. Because really you're just going to have stem 0, stem 1. Leaves, you don't got a 0 on here, so you got 1, 1, so 2 1s. And then how many 2s? 1, 2, 3, 3 2s. How many 3s? 1, 2, 3. So 3 3s. 4. No extra 4s besides this one. 4, 5, and 7. So 4, 5, and 7. And for the 10s, you got 10, 11, 11, and 12. 11, 11, and 12. So, the range is 12 minus 1, or 11. The median, there are how many numbers here? Let's see, we got 8, and then 7. So 15 numbers. 15 numbers means that the 8th number is the one we're looking for. The 8th number is 0, 3. So median is 3. And the mode, how many modes are there? Well, there's 3 2s and 3 3s. Nothing else reaches that many. So modes are 2 and 3. How about this then? We got 3, 5, 1, 17, 11, 45, and 17. Well, we're going to have a few empty stems. 0, 1, 2, 3, 4. And the leaves. So for the 0 10s, so for the single digits, we got 1, 3, and 5. Okay, and for the 10s, we got 11, 17, and 17. And for the 40s, we got 45. So there are 7 data points. The median is going to be the 4th one, so 11. Because we've used this order so far, we'll keep to it. So the range is from 1 to 45, which is going to be 44 for just a numerical range. And the modes, are there multiple modes? No, there's 2 17s, and everything else there's only one of. So mode 17. Okay, how about this one here? Stem 0 and stem 1. For the leaves, we got 4, 5, 6, 7, 8. Ah, but there's 2 7s. So 5, 6, 7, 7, 8. Okay, what about the 10s? Well, we got a 10 and we got a 12. So there are 8 data points here. Always count over all your leaves to make sure that they match the number you started with. Otherwise, you did something very weird somewhere, i.e. very wrong. So, the 8 data points, the range is greatest minus least, so 8. Median, the average of the 4th and 5th ones, which in this case means 7 and 7, so it's 7. And the mode is, well, there's 2 7s and there's not 2 of anything else, so mode is 7. Okay, so let's go on to other forms of graphs. If you put a bar around this leaf, the stem and leaf plot, if you made this into bars, you would have bins of data. You would have categories, like from 0 to 9, and from 10 to 19, and so on. These categories touch up against each other. That is called a histogram. A histogram represents the frequency of data that's been organized into intervals, such as 0 to 99, 100 to 199. These intervals must be the same width, so 0 to 99 is 100 values, 100 to 199 is also 100 values. And they must touch. I mean, technically, these 99 to 100s, there seems to be a gap, but if your numbers are all whole numbers, then yeah, this is effectively touching. So, a histogram is a type of bar graph. You may have seen them being referred to as column graphs before because the bars usually go vertically, whereas regular bars usually are used for horizontal. But hey, that's just an etymological difference, really. It's just a name. So, a bar graph uses solid bars to compare quantities. The bars are the same width, and it's their length, or height, in the case of vertical bars, that shows the difference in quantities. For example, this data in this table with a few students and their number of siblings, if you make a bar graph, what you do is have these different categories be different bars, and the length of the bars indicates the quantity associated with that category. In this case, we also labeled the number on top of the bar, but this is not required. They're just there to make it more clear. that we put a title and we label the axes for what they represent. In this case, the horizontal axis is for the different students, and the vertical axis is for their number of siblings. Because that is the two bits of data that we have that are corresponding with each other. All right, so let's say we have 17 students whose number of siblings have been organized into a table. And we want to make a histogram of this. If these had been, say, siblings 0, siblings 1, and so on, you can still argue that that would still be good for a histogram. Because 0 siblings is approximate. And 1 sibling is right next to 0 if we assume that you can't have half a sibling count as well, a half sibling. So, there are 4 people with 0 to 1 siblings. That means that bar is going to be 4 high along the vertical axis. And the next column, which is 2 to 3 siblings, it's going to be 10 high as per the frequency given. And then the next column is 2, and the last one for 6 to 7 siblings is 1 high. So the different bins of data are about the number of siblings. So on our horizontal axis, we label it siblings. And the number of students with each category, so the quantity associated with each category, is given in the vertical axis. So that's why we label it that way. Labeling axes is critical when making bar graphs or histograms. And of course, titles are important too. Okay, so let's make a bar graph for the data in this table. We have 4 students. They made a number of free throws. Presumably, this is the number of free throws they needed to actually get the basketball into the hoop a certain number of times, like say twice, perhaps. Like most people are not that good at free throws, okay? So maybe it's once, maybe it's twice. But anyhow, the number of free throws taken by these 4 students, we have 4 categories, so we line them up along the horizontal axis and we label it with what the categories are, in this case different students. And then we draw the bars up to a height commensurate with their number of free throws in this case, so the quantities within that category. And we would label the axis with what those quantities represent. And of course we also need a scale to make sure that people know what column size means what. Because, well, you don't necessarily need to label the columns with their quantities. All right. If you make this histogram for the data in the table, the number of people who needed 0 to 1 free throws, 1 person, 2 to 3 free throws, which is the next category over, which touches the 0 to 1 free throws. Come on, you can't take half a free throw. So that's why these bars touch. It's because they are for data that is continuous. Like there's no distinction gap. I mean, red cars and blue cars would be very distinctive. But then, if you specify that red cars are cars with peak reflection of light wavelength, this range to this range, and blue cars are this range to this range, well, the bars would still be far apart because you'd have green cars and yellow cars in between. But if you did that, then that could be a histogram, as opposed to you just tallying and making a bar graph of different colors of cars passing by. So if you're chopping up continuous data into bins to represent it as a bar graph, then you're making a histogram. If you're using discrete data, where the bits of data are categorical and the categories are not continuous, then you use a bar graph with gaps between the columns, or bars if you're making the bars horizontally. Yeah. Okay, so here we have the usual axis labels and title, in addition to making sure that because it's a histogram, our bins are adjacent to each other, i.e. that they are continuous. They represent a continuous stretch of possibilities, possible outcomes, and that our bars touch each other. The obligatory problem-solving section, typical of North American math textbooks. When you're solving problems, a graph can show a visual representation of the situation and help you, well, visualize it, obviously, but help you make conclusions about the set of data. The table below shows the enrollment of students in your high school for 6 years. Estimate the enrollment for the 2011 to 2012 school year. We see that it went up, but then it started coming down, and for 3 years it came down by -1 and -1. So 2011 to 2012 will likely be approx 125. Because 128, 127, 126, yeah, it's pretty clear that it's on a gentle downward trend. We call this extrapolation because you're going outside the domain of the data you have to make a prediction. If you are trying to predict using every 2 years data, like if you had this data point and this data point and this data point, and you are trying to predict where this was, then that would be interpolation. Extrapolation. And interpolation. What's the difference? Like, if you have, say, a trend line, where you measure the general trend of what the data is doing, like, say, on here, you would make a trend line that looks kind of like this. Okay, if you have this line, interpolation is a lot more reasonable than extrapolation, because let's say you're measuring the heart rate of mice, all right, at different temperatures. If you have temperatures from 10 degrees Celsius to 30 degrees Celsius, and you measure the heart rate of the mice, if you're interpolating, you can get a pretty reasonable estimate of what the heart rate might be. Let's say you have the heart rate every 5 degrees. So 10 degrees, 15 degrees, 20 degrees, 25, and 30 degrees. If you want to know what the heart rate is expected to be at about 23 degrees, interpolation is pretty reasonable. But if you extrapolate too far, like say estimate the mouse's heart rate at 5,000 degrees Celsius, no. Like, you're going to end up with something completely unreasonable because the mouse would be turned to ash at that temperature. So, this chart shows the average December temperatures in Fahrenheit over 4 years. Predict the average December temperature for the next year. By the way, this is supposed to be a straight line. It's kind of not that great due to not using a ruler. So if your equipment allows the use of rulers, please do use a ruler. So, predict the average December temperature for the next year. It's probably around 21.5 degrees Fahrenheit because by extending the line to roughly where 2004 would be, we can get approximately where this thing's going to end up, which is at 21.5 or so. Okay, so let's say every 5 years the population of your neighborhood is recorded as below. What do you predict the population will be at the end of 2020? Well, 2005 there were 3,023 people. 2010 there were 3,042 people. Plus 19 people. And 2015 there were 3,056 people. So plus 14 people. Now, what do you predict the population will be at the end of 2020? Yeah, measure out about the right space. So you're looking at around here-ish. And this is reasonably straight, so your trend line would probably be about that. And you can draw a line back over and be like, oh, I expect this to be around 3072-ish. Okay, 3070 is also reasonable, but then that's basically the plus 14 applied again, and you can't be sure about that. So, estimate circa 3072 people. Your neighborhood is growing very slowly, apparently. Graphs can be used to make predictions, as we did just now. A line graph shows trends over time and can be used to predict future events. A scatter plot displays two sets of data on a graph and can be useful for showing trends in the data. In this case, this is a scatter plot that you could also have plotted using a line graph. Because you don't have multiple values for each domain value. A scatter plot is mainly differentiated from a line graph by, say, hours studied versus grade on test. You can have two people who both studied 5 hours, and one of them got a 79 and the other one got an 83. So you'd have two range values for one domain value. A line graph, on the other hand, you only have one range value for each domain value. In this case, it's pretty glaringly a straight line. The scatter plot, the line of best fit, shows that all the points are on a straight line. If the car was loaded with enough fuel to reach the destination plus 50 kilometers range to spare at the fuel mileage seen above, how far is the destination from the starting point? Okay, so if we want to completely run out of gas, 600 km equals fuel exhausted. Fuel exhausted. Therefore, we have 50 kilometers range to spare. That means 600 minus 50 equals 550 kilometers from start to destination. Okay, if the trip started at 80% fuel and was driven at a constant speed on the family trip, how far could the car go on a full tank of gas under the same driving conditions? Well, 600 kilometers equals 80% max range. Therefore, the range is equal to 600 divided by 0.8. So 750 kilometers. The car could go 750 kilometers on a full tank of gas under the same driving conditions. And if you wanted to find, say, how much gas was left at 240 kilometers, well, you would plot that up and plot it over. Or, because the equation of this thing is pretty obvious, as in you spend 10 liters of gas per 100 kilometers, so 1 liter per 10 kilometers, you can also use the equation to find the value. Right, I should probably just demonstrate here what the graphing version looks like. Of course, you should use rulers, please. If you can use rulers, please do. Alright, let's use this scatter plot to answer some other questions. Birds observed in Hyde Park. Bruh, if you only observe 45 birds in a year in the park, those had better be 45 different birds. No, I don't mean different bird species, I mean different individual birds. Because otherwise, that's like saying, oh, this month, only 4 birds were ever spotted in the park. As in 4 occasions was a single bird spotted. This must be a park that's not very friendly to birds. Because in my experience, you see a lot of birds in any decent sized park. But if you're talking about different individual birds, yeah, sure, okay, pretty reasonable. How many birds were there in 2004? Well, presumably this means birds observed, because it's like, how many birds were there? Oh, we don't know how many we didn't see, therefore we can't answer. No, you're supposed to use the data you're given to you to answer the questions given to you, not troll your teachers by being unsmart about it. And I say unsmart because your teachers mark your stuff. That's a big deal. How many birds were there? 45. We can see the point for the year 2004. What relationship do you see between the number of birds and year? Plus 2 birds per year is what we see, because you go from 45 in 2004 to 47 in 2005 and 49 in 2006 and 51 in 2007. Predict the number of birds there were in the year 2003. Well, if the plus 2 per year trend could be extrapolated backwards, by 1 year that's reasonable to extrapolate backwards, so we'd expect there to be 43. But of course, if you try to extrapolate backwards a lot of years, you will find yourself with a negative number of birds, which is completely ridiculous. Predict the number of birds there will be in the year 2008. Well, that's just 1 year past this range. So plus another 2 is pretty reasonable. From 51, that's 53. 53. If the trend continues, in what year will the bird population reach 100? Well, it was 51 birds in 2007. In 2007, plus 2 per year. So, you're looking at in what year? We're not dealing with half years here, so we're looking at you need 50 more birds, so 25 years. 25 years will do it. Therefore, I mean, you might have to show mathematically that, like, 101 minus 51 over 2 or something, or 50 over 2 maybe. So 25 years will do it. So 2032 we'll have the bird population reach 100. Data that's gathered by surveying a random sample of the population may be used to make predictions about the entire population. For example, if you have 5,000 people from a city asked if they thought the town needed dedicated bicycle lanes, separate from road traffic and sidewalk traffic, 3,351 people said yes. 1,504 people said no, and the rest said did not care. Okay, how many people didn't care? Do we need to know that? No. It says predict how many of the 28 million people in the city think dedicated bicycle lanes are needed. Okay, this sounds like a city in China or Japan, because China is the bicycle kingdom, you know? And there are separate bicycle lanes from car lanes in many of China's cities. Which is really nice, because people in bicycles take up a lot less road area than people in cars. So we got, assuming this is representative, so in other words, assuming these 5,000 people accurately represent the proportions in the city, as far as rounding error allows, you have 3,351 people saying yes out of 5,000. This proportion, if it applies to the rest of the city, you multiply by 28 million. So 3,351 divided by 5,000 times 28 million. You end up with 18765,600. 18,765,600 people who think that dedicated bicycle lanes are needed. That's a lot of people. So probably the city, if it can find the money, will want to build said bicycle lanes. Wonderful. Because having bicycle lanes just drawn out on the road as they are where I live in Canada is, in my opinion, exceedingly dangerous for cyclists and drivers, for that matter, alike. Because guess what happens if a cyclist loses control and then the driver swerves? Oh dear. Exercises. In a survey of voters in a small town, 59% of those surveyed said they would vote for Bob for city council. If 21,000 people vote in the election, about how many will vote for Bob? So, you're looking at 21,000 times 0.59, which is equal to 21,000 times 0.59 equal to 12,390. So about this many people will vote for Bob if the survey has accurately represented the population. Of course, calling this a small town is Probably not by North American standards, because like 21,000 voters is a small city in North America. But where I was born, like China, that's not even a large village, really. Yeah, scales differ a lot. So some questions might seem kind of sketchy. Okay, a survey shows that 31% of high school and middle school students buy school lunches more than 3 times a week. If a school district has 9,600 high school and middle school students, about how many buy school lunches more than 3 times a week? This is a pretty small school district, as far as I'm aware. So, 9,600 times 0.31, so 31%. Is equal to times 0.31 is equal to 2,976 students buying school lunches more than 3 times a week. That's the predicted number. The actual number can, of course, be a little bit off from that. So, 8th grade students were surveyed to find out how much they would be willing to pay to go on a class trip. 73% of the students surveyed said they would be willing to pay $11 to $20. If there are 300 students in 8th grade, about how many would be willing to pay for a trip that costs $11 to $20? So, 300 students times 0.73. By the way, this had better be 300 students in one school. So we expect about 219 students willing to pay for a trip that costs $11 to $20. This was a survey. Surveys are usually samples. In other words, we don't survey everybody. If you surveyed everybody, then that's a census, assuming that, of course, that everybody replies. There is a non-response bias, and there are also response biases. But we can discuss that stuff later as we discuss, say, other types of samples. Now, in a sample, you take only a portion of the population, and this portion should be unbiased. It should represent the population proportionately. In other words, it's not like, oh, I know that there are people who like eating at fast food restaurant A, B, and C. And then I go to fast food restaurant C to survey people there about which restaurant they prefer. No, that's obviously biased. In a biased sample, the population is not accurately represented by the sample. The example I mentioned just now is a convenience sample. Other forms of convenience samples include polling your friends who are sitting near you in the cafeteria about their favorite fast food. Because guess what, guys? If you'd just gone out to buy fast food, you probably went as a group to the same place, or some places very close to each other or similar to each other. And that probably indicates you have relatively similar preferences. A simple random sample is you stick everyone's name, so everyone in the population's name, in a hat and draw some names randomly. A systematic random sample, you take the list of names or people, start at a random name or number, and then you pick every 10th name before or after that choice. It could be every 10th if you want about 10% of the population to be surveyed or sampled. It could be every 5th. It could be every 100th. The point is, a systematic random sample, the starting point is random, but then you go systematically. A stratified random sample is that you divide your overall population into several groups, and then you survey the same proportion of each group. Like, say there's 100 teachers and 2,000 students in a school. and you survey 10% of the teachers and 10% of the students about maybe, does the school hallways need repainting or something? Does the school hallways need repainting? Well, then you would be able to get a stratified random sample as long as within each of those you used some sort of random method, systematic or simple. A cluster random sample, let's say you have 1,000 schools and you pick a random 10 and you interview 10% of the staff from each of those schools about some issue or other, such as a change in the curriculum. Convenience we discussed already. Example 1. Look at the following table of an unbiased sample to determine the favorite sport of middle school students. Well, hockey, there were a lot of people who liked that. Basketball, not so much. Dodgeball, oh, there's even more people who liked it than hockey. Probably because even in Canada you can only play hockey in part of the year, whereas dodgeball you can play whenever. Soccer, oh, hey, a lot of students like soccer, more than any other category. So the favorite sport of middle school students is middle schoolers' favorite overall sport of those listed here, that is soccer. Also known as football for most of the world. As compared to American football, which is probably more accurately named hand-egg. Because that's what you do. You kind of hold it in your hand for most of the time. Alright, exercises. Determine whether the given situations represent a biased or unbiased sample, then tell the type of sample. Writers of a popular teen magazine want to write a story about which movies their readers like. The writers decide to interview the first 50 people that walk out of a movie theater. This is a convenience sample. And it is biased. Honestly, we should probably have written biased and then convenience. Why is it biased? Well, what movie happened to have let out at the time the writers went there to start waiting for the first 50 people to walk out? Well, that kind of determines which type of movie is going to be overrepresented in your story. And also, a lot of people just don't like going to movie theaters, so yeah. The student council wanted to raise money for their school by selling homemade cookies during lunchtime. To find out the favorite kind of cookie for the majority of their school, they conducted a survey. They gave the survey to 20 randomly selected students from each grade level. This is a stratified random sample. You can say it's unbiased. Like, you can reasonably claim that this is unbiased. If you took the results you collected and took a weighted average by the number of people in each grade level. Because if it said they gave the students to 5% of the students from each grade level, that would be totally unbiased. This is still stratified random, technically. Stratified random. But what if you had, say, 600 grade 9s, 600 grade 10s, but only 500 grade 11s and 500 grade 12s? Then 20 randomly selected students from each grade level would be biased if you weighed them all equally. If weighting assigned per grade. That's serious business. Would have been better for these guys if they just surveyed whatever percentage that gives a total number closest to 20 per grade from each grade. Yeah. To determine the most frequently used gas station, a researcher randomly selected every 10th person from a drive-through fast food restaurant and asked them where they last filled up with gas. This is biased. And it's a convenience sample. Why is it biased? Where is this fast food restaurant? Because I know that many gas stations actually have fast food places with drive-through counters and drive-through lanes. Something tells me that if you go to said drive-through fast food restaurant, or even one that's actually just near a gas station, you're gonna get, oh, they last filled up with gas, the nearest gas station is overrepresented. So this would not be representative of the population. Okay, misleading statistics. It is said there are lies, worse lies, and statistics. Because you can present statistics in different ways to say basically whatever you want. Graphs can be misleading for many reasons. There's no title. The scale does not include 0. Like the birds we had in High Park before. Yeah, the scale started at a pretty big number. So really it's not that much of a change, but it looked huge. There are no labels on either axis, the intervals on a scale are not equal, or the size of the graphics misrepresents the data. So the line graphs below shows the total hours Salomon, that's not a common spelling of the name, spent doing his chores 1 month. Which graph would be best to use to convince his parents he deserves a raise in his allowance? Explain. Well, this makes it look like the rate at which his total chores done increased over the weeks. It looks like it increased faster. This, it looked like he did less work. So, graph A makes it look like he did more chores. Did more chores. By the scale being different. By scale manipulation. Manipulation. So, exercises. Use the graphs below which show a company's profits over a 4-month period. Which graph would be best to use to convince potential investors to invest in this company? I would argue that graph B is actually better. Why? Because potential investors are not that easily swindled when they don't see units on your profit axis. But obviously the point of the question is supposed to be graph A. Graph A looks like a faster growth of profits. We put a comma there to make it clear that the answer that we're giving is graph A. Reason, looks like a faster growth of profits. Of course, that's not grammatically that great, but, well, can't be helped. Why might the graph be misleading? Oh, hey, we don't have a scale on the vertical axis. No vertical axis scale. No vertical axis scale units, and scale is manipulated. So yeah, you can present statistics in ways that, while technically still true, are intended to deceive the audience or make them think of, well, whatever they want to think, really. Whatever you want them to think. So, that's it for this chapter, which was about data and some basic graphs, which I'm sure the graphs, like bar graphs, you should be familiar with from previous grades. So, see you next chapter.